Within the Mun core team, we feel very strongly about actually using the product that we're making in order to see what we can improve. So one of the things that we're doing is after every release, we actually start making something with the previous release. And in this case, we are going to try and make or recreate Pong. And in particular, we're going to be integrating Mun with Rust. Let's first set up a new crate. This will host all of our different examples in the future, but for now we'll only be focusing on Pong, and the reason for that is that Pong is a very simple game which we can make with the language features that we currently have. Coming up with a game that we could actually use, we're very much limited because at the moment Mun doesn't have a race yet, so any game logic that you're programming would have to be with a minimal set of objects, so you can just program them manually for now. The Rust crates that we'll be using are GGEasy, which is a Love 2D-like game engine with batteries, and we'll be using the Mun runtime version 0.2. When creating a Mun library and the host application that actually allows running more complex behaviors, there's a general pattern that you'll probably follow. You'll have to think of the data that actually will need to be marshaled from and to the host languages in Mun, and this will allow you to handle some of the behavior within the host language. In this case, all of the rendering will be handled by GGEasy as well as input handling, and then the barrier between the two will consist of sending game state, in particular the position of the two pedals and the ball, as well as the game score. And these will then be converted into graphical objects in the Rust code. Let's set up the GGEasy environment that we'll need in order to run a windowed game. Then we'll also need to build a Mun runtime, which will be used for launching and updating the Pong Mun library. And this will contain all of our game logic. We can use the invoke function macro in order to call functions within the Mun libraries, and the runtime will do runtime checking that the types are correct. This does mean that we have to annotate the appropriate types, such as in the case of a struct, we'll need to annotate the return type with the struct ref type. And in this case, we are waiting for the invocation to finish, and what this allows us to do is if there are any issues with the invocation, such as type errors, then the runtime will continuously try to see if there's an update to the Mun library, and if the update contains the correct types for the invoked function, the logic in Rust will proceed. So this allows us to, within a specific point, try to hot reload code, and this allows us to avoid panics in the case where you would do an unwrapper and expect on the result of a function invocation. GGEasy works with an event handler trait. Basically what it does is you continuously run an event loop. First you invoke an update function, and then you invoke the draw function, and you can separate your update and draw logic within those two. Within the update function, we call a update function that is inside the Mun library, and after that we update the runtime, and this allows the runtime to check for potential updated files and hot reload the corresponding Mun library. And it's time to create our pong.mun file, and we actually have a Mun extension for VS Code that will at least give you syntax highlighting, but for now that's the only functionality that we have, which is quite limited. So for our Mun version 0.3.0 release, we're actually working on a language server with some basic functionality to improve the editor experience. At the start of the application, we'll want to create some state for the Pong game that we'll keep throughout the game, and we'll use the new state function to initialize this. And we can actually use this throughout the entire application and keep it in memory, and every time the application gets hot reloaded, whether the struct layout changes or not, the application can just keep running, and the Mun runtime will handle memory mapping. At this point, all we'll see is a white screen, which is actually because we are not presenting the context to the graphics card. So let's add some of the basic drawing code that we need in order to render the paddles, then the ball, and the score text, and then also present all of that to the graphics module. The way we are doing that is we put all of the logic with regard to the positions of the different objects in the Mun code, and then we will marshal that to Rust. So first we'll need to implement a value struct vec2. What that means is a value struct is copied or moved into a new function as opposed to garbage collected structs that Mun supports, which are always passed by reference. And then we define a paddle struct, which is garbage collected by default, to have a 2D position and a score. Then we add the left and the right paddle to the Pong state. Somehow we also want to maintain some global settings with regard to the dimensions of all of the different objects. And we want those to be accessible both in the Rust host program and within Mun itself. In this case, I chose to use functions that can be accessed from both Rust and Mun. Then we add a ball. The ball consists of a 2D position and a 2D velocity. And we also add the ball to the Pong state. Now that all of our structs are defined and ball has been added to the Pong state, we actually need to update the Pong state constructor, new state, and to do that we'll be using two functions to construct the ball and paddle respectively. The paddle constructor will have to differ for the left and right paddle, so we'll be giving it an argument position that is assigned to the respective paddles. For the ball, it's all constant, and we'll initialize everything to a origin or 0, 0 position for now, and then once we actually have all of this integrated with the host application, we can start experimenting with what the right positions would be for the paddles, and do that much more easily once hot reloading is actually turned on. As you can see, I actually forgot to turn off the host application, but it just kept running fine. It hot reloaded the code, but as there's no actual logic in the update function yet, there is no change in what we're displaying. Time to hash out all of the drawing logic. So let's first obtain the ball and left and right paddle from the game state. We can simply use the Mun marshalling functionality for this. Here, once again, you have to specify the type that you're trying to marshal such that we can do type checking at runtime. And then the way GGEasy works is they have a mesh builder which allows you to construct a mesh which can be reused across several draw calls. So in this case, we'll have to create the ball mesh, and then we have to create the paddle mesh, and the paddle mesh can actually be used for both paddles but drawn at different positions. GGEasy, when drawing a circle mesh, requires a tolerance, and I'm not really sure what value is going to be useful, so let's just add that to the Mun library API such that we can experiment with that once we're hot reloading and tweak it on the go. The rectangle mesh creation is based on a rectangle bound, which we can easily obtain by marshalling the pedal width and pedal height from the Mun library. Now that we have the meshes, we can do the actual draw calls. As you see, we need the mesh position, and in order to marshal the vec2d, let's just create some code in our library that we can reuse across certain examples for marshaling a 2D vector. We're passing in a opaque struct rev, and then we assume that it contains a x. There you go. That's drawing of the ball and the two paddle meshes. Let me just clean up this code a little because the code duplication is bothering me a little bit. With that done, let's move on to drawing of the two text scores. Drawing text can be quite expensive, so the way that GGG deals with it is there's the option to queue different text, and you then batch those together and draw them all at once. So let's implement that. To support drawing of the text scores, we'll need to add the two public methods that you just saw, left score pause and right score pause, and those can then be used to change the positioning of the score text from within Mun. Everything is looking good so far. Most of the host application bindings that we'll need are implemented now, so we can start the host application and then just keep editing the Mun library in order to change the gameplay logic. As you can see, drawing is working. The pedal is currently being drawn at the left top corner, and actually the other paddle is also behind it, so all of the things are still being drawn at the origin or the 0, 0 position, as that is what we set in settings. To calculate the positions of the different objects within the window, we'll be needing the screen width and the screen height. By default, GGZ fixates it to 800 by 600 pixels if I recall correctly. So let's take that as a base point and then calculate the ball in the center of the window and the paddles on the center left and right left with a little bit of inset. We'll also want some logic for resetting the Pong state. In particular, we only want to reset the position of the paddle because whenever we reset, we want to keep the scores. Let's reset the state in order to get the changes to the ball position into effect. And there we go. Our first rendered game object in a correct position using hot reloading. Let's play a little with the tolerance. As we decrease the tolerance, it seems like the edges of the circle are getting a little bit more smooth, and 0.01 seems like a fairly good parameter for that. Let's also move the two paddles into their proper positions, and then we'll have a good starting point for our Pong game to add the actual logic of the ball with bounces and score into. Then the last thing that we'll have to do in terms of positioning is to put the score text at the quarter and 3/4 marks, and let's also give them a little inset so they're not propped up against the top of the screen. time to implement some of the ball logic. The first thing we'll need is an intersection function for the ball and the paddles. And since this is more for illustrative purposes and not for accuracy, let's just implement an intersection function as though the ball has a bounding box around it, and then we can just do an intersection between two rectangles. Now that we have the intersection function implemented, we can check whether the ball is colliding with the paddles, and if it does, we can flip the x velocity and move it in a different direction. Then we set a default velocity for the ball to just move to the left for now, and then down the road we can actually turn it into a random direction at start. Obviously, for that to work, you actually need to update the position using the velocity. And once that's done, yes, we have a moving ball, and when it intersects with the two paddles, it bounces. As I said, next thing on our list would be to give it a random starting direction. For that, we actually do need to reload the host application since we're inserting an extern function. And the thing with extern functions is that the host application needs to tell the runtime what that function is. So unless the host language is also hot reloadable, you'll always need to restart at this point. Instead of crashing when you try to hot reload a Mun loop that now requires an extern function, it will actually log the error to the console and fail to hot reload the new Mun loop and keep working with the old library that was there. But for this to actually work, as I said, we'll have to restart the application, so we'll need to add the insert function in the runtime builder, and add an actual extern C function as our ABI works with the C ABI. And once that's set in place, we can rerun cargo example and see the random number generation at work. Unfortunately, we're not yet detecting any bounces with the periphery of the game, so it is now just wandering off into voidless space. There you go. One more item checked off. It's possible to score points now, so all that's left to do is get moving paddles and collisions with the top and bottom walls. To implement the moving of paddles, we'll need to do some binding of input. So we'll have to shut down the game again and implement some code in Rust. And once that's done, we can tie that into our Mun code and actually add the game logic for that. So the concept is pretty straightforward here. We'll use the W and S keys to move the left pedal up and down, and the up and down keys to move the right pedal up and down. If both keys are pressed, we'll just keep it in the same position. And voila, we have moving paddles. And this is one of those examples where hot reloading really shines. The game is a bit too slow, and to make it a little bit more fast paced, what we can do is we can just add a multiplier. Whenever the ball hits one of the paddles, it speeds up, and we can just tweak with the starting velocity. It seems that when the paddle moves up or down when the ball is already partially past it, it will get stuck inside because we keep doing the collision check even when it's already inside it, which is exponentially increasing the speed of the ball. And this is one of those good things where the logic is sound. There's no compiler errors whatsoever, but there's just a flaw in the game logic. And as you can see, we can easily debug and then provide a fix for this issue while never actually having to leave the game editor. So especially with complex state that results in a bug, it's very easy to use hot reloading in order to fix one of those bugs on the go.